And what's going on, Matt? 2? We got lesson 1.2.4, describing a graph. All right, today we're going to look at a bunch of different graphs and then just kind of talk about their characteristics that they have. So right here on 1-56, we're going to write down what some of the characteristics that we're going to look for are. First characteristic that we want to find is the function family. Now, function family means, is it a linear graph? Is it a quadratic? Is it exponential? Is it absolute value? Is it a step function? You know, a whole bunch of stuff like that. So the family of equations that it belongs to. So that's what we're talking about when we say function family. Next thing we want to talk about is it an increasing or a decreasing function, or maybe even both? So does it increase? Does it decrease? Or does it even do both? Does it both increase and decrease? We want to talk about whether it's discrete or continuous. Discrete is when we have just points on the graph, and continuous is where we've connected all the points together. Is there some kind of symmetry going on in the graph? So does it have rotational symmetry? Does it have reflectional symmetry? That kind of thing. Symmetry, I don't know how to spell. I think that's how it's spelled. We might want to talk about if it has, what kind of shape it makes. When we say shape, usually we're looking for whether it's made up of a straight line, if it's a curve, or if it's even a step function. Step functions are the ones that kind of do that. So that would be like a step function right there. We want to talk about the intercepts. Let's see, is that everything? Let's see, we might also say, is it a function or is it not a function? And maybe if there's any asymptotes. Is there two S's with asymptote? I'm just going to go with one. So yeah, that's what we're going to look at. So if you're in class, what we would have done is each team would have gotten their own graph, and then as a team, you would have tried to describe your characteristics of your graph and describe them in such a way that maybe somebody else could actually draw the graph without even seeing it. That's what we're going for. Can we describe the graph so well that somebody else can draw the graph without seeing it at all? So we're just going to look at them, all of them, and just talk about each of these things as we go through the graphs. So I'm going to kind of leave this at the top so that we can remember what we're looking for. We won't probably do all of them. We'll just do several of them so you're going to get a feel for what we're doing here. All right, so here's graph A, function family. That's a linear function, straight, increasing or decreasing. From left to right, as the x is increasing, the y is increasing, so that's an increasing function. Symmetry, it doesn't have reflectional symmetry. I can't reflect. I mean, I guess I could reflect off of a perpendicular line right there, so yeah, I guess that's technically true. 180 degrees rotational symmetry. I could spin this 180 degrees, and it'd be the same shape. You can see here it's still going up. But then it would be down below, though. So, no, that doesn't have rotation. If it went through the origin, I guess I could. It's facing the right direction, but it'd be too far down if I rotate 180 degrees. So, no, it's not going to have rotational symmetry. So, never mind. Shape, it's a line. Intercepts, it's got an x-intercept here at -2. It's got a y-intercept here at 1. Function, not a function. That is a function. It passes the vertical line test, so it's a function. Are there any asymptotes? No, asymptotes are usually with exponential functions. All right, so using those descriptions, if I wrote them all down, you could probably make my graph if I wrote those descriptions down. Oh, domain and range. That's the other thing. So another thing I might have said is domain and range. So the domain is all real numbers and the range is all real numbers for that one. Graph B, okay, the function family. You probably haven't gotten to these, but these functions are made by making square roots. So this is like a square root function. Increasing or decreasing, from left to right, it's increasing. You can see that it's going up as we go left to right. The y's are increasing. Discrete or continuous, this is continuous. Everything is connected. Symmetry, not seeing any symmetry. Let's see, it's a curve. Intercepts, looks like it has an x and a y intercept at 0. So the x-intercept is 0 and the y-intercept is 0. Function or not a function? It looks like a function because it passes the vertical line test. Asymptote. Remember, asymptote is when it's approaching a line but never makes it to that line. And I don't see any asymptotes there. Domain and range. Looks like the domain, it only appears over here, so the x values would be anything equal to 0 or greater than 0. So we would say the domain is x is greater than or equal to 0. Range, it looks like it's only up here for the y values. So my y values can't be negative. So I would say my y values are greater than or equal to 0 as well on that one. All right, next one, graph C. We would probably say that this is a quadratic function because it's that nice U shape right there. But this is kind of a weird one. It's a quadratic on its side. So instead of like y equals x squared, this one would be x equals y squared instead. Kind of goofy. Increasing or decreasing. This one is actually doing both. On the top part of the graph, we can see from left to right it's increasing, but on the bottom part of the graph, from left to right, it's decreasing. So it's doing both. Discrete or continuous, that's definitely continuous. Symmetry, there is reflectional symmetry. If we go across the x-axis here, we can see that it reflects across itself. Shape, it's definitely a curve. Intercepts, it looks like we have two y-intercepts, one at 1 and one at -1, and then I've got an x-intercept over here at -1. Is it a function or not a function? It's not a function. It fails the vertical line test. I can draw a vertical line and it's going to pass through more than once. So it's failing that test. No asymptotes. And the domain, I would say, is any number bigger than -1 or equal to -1 because our graph doesn't come back here for our x values. So I would say from here is my domain. So I would say x is greater than or equal to -1. For my range, it's going to keep on going up this direction. It's going to keep on going down this direction. So my range would be all real numbers for this one. All right. And now we finally have graph D, which is discrete. We've seen all of these ones were continuous, meaning all the points are connected. Over here, we only got individual points. So this is what we call a discrete graph. Let's see, 1, 4. So this one looks like the function family is going to be quadratic, but it's only like half of the U shape. I can tell it's quadratic because quadratic you square stuff. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So you can kind of see that pattern there that's happening with squaring. But I'm not getting any negative numbers here that are being squared. When we talk about, we already said it's decreasing, but this is increasing function. From left to right, it's increasing. What else did we say? Shape, it looks like a curve. Intercepts, there's an x and a y-intercept at 0. Function or not a function? It's a function. It passes the vertical line test. No asymptotes. Domain and range. The domain and range is weird on this one since we only have these 4 points. Our domain is going to be only the x values that I see. So there's an x value of 1, an x value 2, an x value 3, an x value 4. I've only got those x values, 1, 2, 3, and 4. For my y values, I got a y value of 0, a y value of 1, a y value of 4, and a y value of 9 up there. So my range would be 0, 1, 4, 9. Let's skip over to graph F. Graph F, we've got the function family. This looks like a combination of linear and step. You know, it's kind of like a linear function here, but it's definitely a step function where it just jumps. It stays the same and then it jumps up to the next one, it jumps up to the next one, jumps up to the next one. It looks like it's an increasing function from left to right. This one, discrete, continuous, we would actually call it step instead. It's like a combination of discrete and continuous. When we talk about the symmetry, I don't think it has symmetry. I'm trying to imagine it being flipped around, and I don't think this one has symmetry. So there we got that. Shape, we'd say it's definitely a step function. Intercepts, looks like it intercepts down here at the y value of -1, but it also looks like it intercepts at 0 for that. And then it looks like it's intercepting the x all across this part. So from 0 to 1, it looks like it's intercepting right there. I'm talking about this right here. It looks like it's intercepting from 0 to 1. So the x-intercept is kind of weird on that one. Domain and range. Our domain, it looks like it's going to be all real numbers if this continues forever, side to side. But our range is kind of weird because our range has -10, but it doesn't have any of the fractions between -10 and -9. So we would probably say that the range is integers. Integers meaning that it's only going to be whole numbers for the range. We're not going to get any fractions on that one. That's kind of a weird one. A couple more. Let's just do these two right here. So this one, we can see that it's a decreasing function. If I had to guess on this one, I'd say this is exponential. So I'm going to say this is an exponential function. It's discrete because they're all made of points. I'd say that the intercept right here, the y-intercept is 8. It doesn't look like it's going to have an x-intercept, but it is going to have, I think, an asymptote. I think that it's never going to get to this line here. So we'd say that the asymptote is y equals 0. So it looks like it's getting really close to this line, but it's going to approach it and never actually make it there. So it looks like it has an asymptote on that one. No symmetry on it. Yeah, that's good. All right, K, or is that H? That's H. H. This one is, the function family is absolute value or linear absolute value. So when we get these V shapes, these are linear absolute value. They're made when you have an absolute value in your equation. So looking at the increasing or decreasing, this part of the graph increases. So from left to right, we can see that our y's are going up. From left to right, now we're going down on this side. So this one decreases and it increases at the same time. So we've got a y-intercept of -3. We've got x-intercepts of +3 and -3. And the shape, we would probably say it's made up of lines instead of curves. Symmetry, yeah, there's symmetry going down along this line. If we reflected over that line right there, we would definitely have some symmetry, some reflectional symmetry going on there. Our domain is all real numbers. Our range, this is the lowest point right here. So our range is that number and any number bigger than that. So we would probably say that its y is greater than or equal to -3 for that. All right, so the goal in class would have been to describe it and then try to give it to somebody else to see if you described it well enough that they could actually draw your picture just from your description. So when we do that, we're looking for the characteristics. What makes this different from all the graphs? We can skip that one. We can just skip that one. Here we go, 1-59. Okay, so we've got 3 graphs over there, and then we've got situations, and we want to match up which one goes with which one. The price of a postage stamp over 20 years. Which graph would do that? Well, I don't think the price would go up and then go down for postage stamps. And I don't think postage stamps are going to go down. Now, this is an interesting one. It's a step function here. And it kind of makes sense because for a while, the price would be this much. And then all of a sudden, they raise the price. And then it's this much for a while. then all of a sudden they raise the price and it's this much for a while. So you can kind of see where step functions would come in, where things stay the same for a while and then change all of a sudden. So prices do that a lot. Price is a really good way to do a step function. So this one would be I. There you go, I for that one. Whoop, right there. The number of hours of daylight each year over the year. Okay, so if this is January, we don't have a lot of daylight. And then June, we've got plenty of daylight. And then December, we have less daylight. So this is probably a better one because this one increases and then decreases when we're going from January through December. So I would say that this one would be I. The value of a car over 10 years. And this is kind of exactly how cars, what we call depreciate over time. Their value goes down really fast at first, and then the older the car is, the slower the value goes down. So when you buy a new car, yeah, you lose a lot of value in the first couple of years. So if you got a used car, your value is not going to change as much. So I. All right, last part. Why are the following not enough to describe one of the graphs below? Discrete. If I just said find the discrete graph, you wouldn't know which one it is because both of these are discrete. So I and I. I don't know why we have I's in here. So those two graphs are both discrete. Linear and increasing. Well, that sounds like it's this one, but this discrete graph over here is also linear and increasing. So that's not enough to tell which one we're talking about. So I and I are both linear and increasing. Last one, nonlinear and decreasing. All right, so this one is nonlinear because it's a curve, and from left to right, it's going down. This one is also a curve here, and from left to right, the y values are going down. So I and IV have those two characteristics, so that's not enough. All right, so you see that when we describe a function, we have to go into several details if somebody wants to reproduce what we've described. That's all I got for you. Math hard. See you later. Bye-bye.